Hello everyone, I guess we can start now. अन्वित तूने recording चालू किया ना?
Yes, I've started the recording.
Yeah, cool. I guess we can start. Yeah, just turn on my camera. Yeah. Hello everyone, I'm Arnav Jaiswal and welcome to this session on image processing with SiriL and Gimp. So today it'll be a really exciting session because we'll be actually processing the data which is available on the internet to process Pillars of Creation, which is one of the most iconic images the Hubble Space Telescope has taken. So before we actually get started with the practical, let's just learn some basics of how of the theory of the image we are going to process now, because there's no point to just learning the steps because anybody can just do the steps. So we'll just look into the basic theory of what we are doing when we are actually processing the image. So let me just share my screen. Uh, yeah, is my screen visible?
Yes, it is visible.
Yes.
Yeah, so just a sec.
Okay, now it isn't actually, like it was a while
अच्छा
ago.
अच्छा just a sec. I think मैंने गलती से close किया. Just a sec. Yeah. हाँ. Now.
Yes.
Yeah. So yeah, let's just look at the brief theory behind image processing with SiriL. So let's start with what frames are. So what are frames? So frames are just basically different types of images which we will capture to make our astro photograph the perfect image. So there are a lot of different types of frames as we'll see in the next slides. These frames are useful because, well, they improve the image quality of the image by accounting for various noise and artifacts in the image. They help you reveal fine details which are usually lost if you don't have multiple types of frames. And also, when you take images, there's a lot of sensors and camera work which goes into an image. So when you actually use the different kinds of frames, they compensate for the imperfections in the optics and the sensors of the frame. Of the final image. So this is basically why we need different types of images. So let's head into the first type of frames, which are the light frames. So light frames is basically the primary image of the astronomical object you're photographing. Like if you're just sitting on a field and just taking the photo of the sky directly, the photo of your sky, it'll probably look like what's on your left. I mean, it's there's like some dust on it. It's not the perfect color. It's kind of blur. So this is how an actual photo looks like. So this is what you take with the camera. So they are like the actual images of the sky which the camera will take. So and all the other frames which we will discuss in the presentation will be just to remove all the errors from this frame. These frames are long exposure shots. Exposure is the amount of time the shutter of the camera is on. So while you take these photos, you usually keep the shutter of the camera on for a pretty long period of time. It can range from almost like 30 seconds to a minute. And this is basically light frames, which is basically just the image of the sky you take directly. Then let's go to dark frames. So basically, when you take images of the sky, there's certain noise which is caused by the circuitry of the camera. This noise is temperature dependent, and it is called as a thermal noise. And thermal noise is so dark frames are basically taken with the camera with the cap on the lens of the camera. By this, no other external light enters, and you just take a long exposure photo with the same settings as a light frame, and you take the photo just to capture the thermal noise. And this thermal noise is later subtracted from the final image to to have a better type of image. So this is basically about dark frames. Then there's flats. So oftentimes, I'm sorry. Yeah, so oftentimes there's noise in the final image due to dust particles and detector issues. So dust particles usually just accumulate on the camera and lenses, and it can cause these horrible looking fringes and stuff on the final image. And there's also vignetting which can occur which is basically the reduction of image brightness on the periphery, which happens when you're taking images, because well, lenses are spherical and uh, there can be reduction of brightness on the edges. So to counter all of these factors, we need flat frames. Flat frames are flat frames are captured by evenly illuminating the entire field of view, and you can do this by multiple ways. As you can see down here, you can just like cover your lens with a t-shirt. The t-shirt is translucent, so it it disperses the light equally, and also it illuminates the light pretty evenly. So basically, the flat frames just capture the noise pattern and the vignetting effect of the lens, and you can later subtract this from the final image too. And then there are biases. So biases account for the electronic noise in the image. So when we measure, so to measure this noise, you just have to take like photos with really short exposure time and in darkness. You can see an image of a single bias on the left. It's just kind of like one of those TV screens which you see when you press the wrong buttons. So yeah, that is what this measures, and just measures the electronic noise of an image. You may have a doubt, what's the difference between biases and darks? The difference is darks usually measure the thermal noise and also account for the vignetting, and also sorry, the darks are usually account for the thermal noise, which is caused by long exposure shots, and biases are usually accounted for the short exposure shots and for the electronic noise. So this is about the basic types of frames which we capture when we take images. And here's a really nice example of, just different frames and coming together to make a really nice final image. So this is a light frame, the flat frame, the dark, and the biases. The darks and biases are unstretched, that's why they look dark, but there is some detail in them. And when you just finally combine all of them and process, you get a really nice photo of a nebula, as you can see here. And yeah, this is about frames. And before we actually start with the presentation, let's just look into one last concept called histograms, because we'll be dealing with histograms as we process images. So what is a histogram? So basically, when any image you take, each pixel in the image is given a number from 0 to 255 depending on the bit of the image. But for an 8-bit image, it's 0 to 255, where 0 is pitch black and 255 is bright. So basically, histogram is just a representation of the number of pixels at each digit. As you can see here on this graph, like there's a peak at 64. So basically, the most number of pixels are at the number 64. So the x-axis represents the range from black to white, and the y-axis shows the number of pixels at each tonal level. So this is what a histogram is in the context of images and image processing. Then why are we learning about these histograms? This is because of a concept called histogram transformations. When histograms are initially presented to you, they're on linear mode, as in it shows pixels directly. It shows the count directly proportional to the number of pixels at each brightness level. But well, I mean, it's pretty obvious when you take a photo of the sky, the most of the sky is just dark. And so when you take an image, most of the pixels are going to be dark, so you're not going to get a really clear idea of how the object you're trying to capture looks like. So that's why, to for us to visualize the data better, you need to do this thing called as a histogram transformation. So transformations in general is just changing the y-axis of the graph by applying certain mathematical functions, and this can help us visualize the data better. So again, histogram transformations is not changing the data. It is just applying a mathematical function to the y-axis so that we can visualize the data better. Because most of the sky is dark, so we need a way to visualize the lights of the data better. So let's visualize histogram transformation. So let's say in the graph before, you have a million pixels at a value 10 and just 1,000 pixels at a value 200, which is, I guess, kind of a realistic image of the night sky, because most of the pixels are going to be dark. So if you just draw a linear graph, I mean, you can see it's probably going to be like a huge peak at 1 million, and it's just going to be really small at 1,000. So the million bar will be 1,000 times taller than the 1,000 bar, just because it's linear. But say the y-axis is not actually just the number of pixels, but it's a logarithm of the number of pixels. Just take log million and log thousand, and you'll see that log million is just 6 and log thousand is just 3. So instead of the graph being like this, the graph will be like this. Like it will have a peak, but the peak will be much less significant than the peak you have in the linear image. And there's certain more functions. There's a square root function where you can take the square root of the y-axis, where it'll be like 31.6 times taller than the 1000 bar. So you can see how this data is compressed in quotes. This is because, and when you compress this data, it just brings out a more uniform graph than the linear graph. And this gives rise to an image which is clearer to visualize, because when you have a peak which is shorter than the linear peak, it's more evenly spread out. And when it's more evenly spread out, the program helps us visualize the light pixels of the image in a much in a with a higher intensity than you can in just a linear image. As you can see on the graph on the left, like in linearly, I mean, the light pixels and the image is just not as clear as, say, if you apply a logarithm function on the y-axis, where the details really come out. So this is about histograms. And let's just look at this last part about how telescopes capture images, because that is what is our the most important part. So obviously, you might have known because you've read the modules before. Images which telescopes capture aren't in the beautiful red and purple and blue colors which we see them to be. Space telescopes actually capture different images based on wavelengths of different elements and their electrons moving from different shells. So that is what space telescopes capture. So space telescopes capture a lot of these types of images, but for today, let's look at the most famous type of images the telescopes capture is called the SHO or the Hubble palette. There are a lot of different permutations and combinations of colors you can tinker with, but let's just look at SHO for now. So the SHO, the S stands for sulfur 2. The sulfur 2 is emitted by ionized sulfur. And in astrophotography, we usually associate it with R or red. And then there's the H alpha, which is emitted by excited hydrogen atoms, which is associated with green in the SHO palette, and O3, which or oxygen 3, which is emitted by doubly ionized oxygen atoms, which is associated with the blue color. So we assign colors to each of these images and we make our final image. You can see the wavelength range on the left, of the O3, H alpha, and SI. SI will have the most will have the highest wavelength of then followed by H alpha and O3. So basically, the Hubble Space Telescope captures data in this wavelength, and it makes different images, after which you process them to make your final image. So this is how the Hubble Space Telescope captures images. And now that we are done with this, let's actually get started with the practical data. So just a quick recap, we learned about different types of frames. We learned about histograms and how to transform histograms so that we get a more clearer output of the image. And we also learned about how space telescopes capture image and how they're not the beautiful colors we see them to be, but they're just elements of different wavelengths which we assign colors to. So does anybody have any doubts before I get started with the practical demonstration? Uh, I guess we can get started with the practical demonstration. I mean, we can have doubts later, I guess. So yeah, we'll start right from scratch. So if so, like, where do you want to, from where do you get the data you want to obtain? So what Hubble does is Hubble has its database of the images it has captured before 2017 called the Hubble Legacy Archive. So you can just Google Hubble Legacy Archive and just click the first link and you can enter the site. So basically here you have all the different types of images Hubble has captured in its history since from almost 1990. So today we were going to process the pillars of creation. So just search pillars of the code for pillars of creation is M16. You can just search for M16 here, and you can search. It'll just take a couple seconds to load. Yeah, and So you can search, you'll see all these different images. You can click on images and you can see all these different types of images provided by Hubble. And for us, we'll be dealing with the pillars of creation. So we'll be make sure to select this image right here, the fourth here, and then you can click on the blue link right here, and it'll add your image to the cart. Then after you add your image to the cart, just go to your cart and you'll see this file in your cart, and you can then download it as a zip file. I mean, and you can just fetch the data and you can download it as a zip file onto your computer. You can save it anywhere you want. You can unzip it, do whatever you want with it. So yeah, that's how you get the data in the first place, and that's how you can get the data. I mean, the files are pretty big, almost like 250 MB for each file. So I have downloaded each file just before so that we save time. So let's go ahead and see what you do with each of the individual images. So this is SiriL, the interface I've opened. This is called a SiriL. You can it's free to download. You can just search SiriL and it'll show up to download on your software. And yeah, so you can just download SiriL from the internet with a quick Google search, and this is how SiriL looks like. So what you do in SiriL is first on the top left, there's an open tab. You just click on it and you open the three files that you have downloaded. So the three files you downloaded are .fits files, and you can see most of them just by name they look the same, except they have the wavelengths of the light in which they're captured in, and it's 502, 567, and 673. I think you can recall that the 502 will be the blue, the 673 will be the red, and 657 will be the green, and we can associate it with the SHO palette. So like 673 will be the sulfur, the 657 will be the hydrogen, and the 502 will be the oxygen. So that is how we associate it with each of the files. And so let's just open one of these files. Let's start with the sulfur file, and let's open it. Yeah, so SiriL will open it. I mean, you see it first, and you basically can't see anything here, except maybe like one or couple of these stars. This is because, as we saw, the image is in linear, as you can see at the bottom here. Image is linear, so image it just shows the real pixel values, which are so, and the real pixel values obviously is going to be mostly dark, just to recall. That's why you can't see too much of the image. So what you do is you apply histogram transformation, as we saw. The histogram transformation we'll apply is this transformation that SiriL has inbuilt, and it's an inbuilt function. And we won't go into too many details of that function, but yeah, it's an inbuilt function which will help us transform. So you go to image processing right here, and there's histogram transformations. So yeah, on the histogram transformation, you click on this rightmost settings button, apply auto stretch algorithm to image. So yeah, you can just click on it. Oh, and you'll see almost like magic. The image is much more clearer to see. So yeah, you just apply auto stretch once, and this is the effect. So you apply it. Make sure to apply it 2 or 3 times, because sometimes the when you once you apply it, if you apply it 2 and 3 times, you get a much clearer output. So yeah, I'll apply it just once again, and yeah, I applied it once again. So yeah, so this is the image of the 673 nanometers. And after you are happy with it, you just apply histogram transformation 2 to 3 times. You click on this button right next to save, which is called save the current image in a different name. Not the save button. It will just save as a fits image, but we don't want a fits image. We will have to save it as a different name. And yeah, so I'll just save it right here into the folder called M16. And this is SI, so I'll just call it M16 SII. And uh, just a sec. I'm so sorry for the interruption. I'll just be back in 2 minutes.
Meanwhile, if you have any question related to any topics that have been studied till now, you can put them in the chat or just ask on the mic. Anvita is also here. He will answer your questions.
Yeah, I'm back. I'm so sorry for that, but yeah, let's just get back to it. Yeah, so we were at saving the image. Anvit, is everyone still here?
Yes, yes. No one left
Yeah, yeah,
actually.
I'm
Yep.
so sorry for that. Yeah, yeah, I'm back here. So yeah, we were at saving the image. So yeah, because we were at, just to recap, 673 nanometer. It's which corresponds to the S in the Hubble palette. So we'll save it as M16.SII. But while saving it, we'll save it as a .tiff file. .tiff. Sorry, that was a comma. .tiff. So yeah, we'll save it as a .tiff file. And once you save it, we'll save it as a .tiff file because I'll explain it later. But yeah, we'll save it as a .tiff file. So once you save it, yeah, you can save it as 16-bit, and yeah, it'll be saved as a .tiff file on the folder of your choice. And once you've opened this, let's just quickly process the other two images in the exact same way we did. This is 657, so this corresponds to the H alpha. So again, go to image processing, go to histogram transformation. I just apply the transformation a couple times. This you'll need to apply a couple times because even in the first transformation, it's so faint, it's almost not noticeable. So yeah, the first time, and then you apply it for the second time, and yeah, now if you apply it for like a couple more times, it's just a much more clearer image, as you can see. So this is for H alpha. Let's just apply it one more time just for, and yeah, I think I'm happy with that. And you will save it again as in the folder of your choice, M16 HA TIFF. Yeah, here we'll save this. And let's process the last image. Mm, yeah, the 5021. Yeah, and yeah, I had actually pre-processed this image, so I think that just saves our time, and I'll just save it as M16. Wait, just a sec. Uh, M16 O O3.tiff. Wait, I just 16-bit save. Wait, I think I just made this error. I just saved one of the files by mistake as a fit file. I don't even know what it is. I'll just change that. Uh, I'll just change that. Yeah. So sorry for that. If yeah. So now that we have our three TIFF files, we can finally go ahead and apply color to them. So the way to go up to go and upload color to them, it's a really nice way on SiriL. You just go to image processing again, and you have this setting called RGB compositing. You go to RGB compositing, and there you'll see different colors. So you have red, green, blue, and let's just recall our palette. So R stands for the S2 in the Hubble palette. So you go here, and yeah, you go to the folder, and yeah, you have S2 here. I think it's just loading. Yeah. Then for green, you have H alpha. Yeah, and for blue you have the O3. And yeah, so once you've applied all of these, you can just go shift into the RGB frame, and this is the image you get. I mean, if you compare it with the actual image, it's actually pretty comparable, which is really cool because it's so easy to do it. You just process the three different images you have gotten from the Hubble data, and you just assign different colors to different types of images, and you get this finally processed image. And I mean, you can just go ahead and crop it, because I mean the edges are not really neat. So I mean, cropping is just left clicking and selecting the part of image you want. You can then just right click, and you'll see the crop option right here, and this will, yeah, crop the image. So yeah, this is the final image you get for pillars of creation on SiriL, which is, I think, pretty cool in its own merit. But the thing with SiriL is that SiriL is not really good if you want to manipulate some details. Like you can see, like some of these stars are just maroon, and maybe that maroon is something you don't desire, because I mean, you just maybe want a fainter shade of pink there. So so it's really hard to do all of that stuff on SiriL, because SiriL is just a little closeted in that matter. So if you want to actually process astrophotographs in a much more detailed way, you use this software called GIMP. And I have GIMP. GIMP is again an open source free to use software. You have GIMP right here. Yeah. So GIMP is short for GNU Image Manipulation Program. Yeah, so this is GIMP right here. So GIMP basically works in a similar way as SiriL. Let's just open the three images which we have. Let's go to File, and File. You not don't select Open. You select Open as Layers. So you go to Open as Layers, and you will select the three images. You will select this. Wait, open, and yeah, let's open both of these. Yeah, and I guess they're just opening. It takes a couple seconds to open. Yeah, and you once you open the three of these images, you can just manipulate them in a lot of ways, which give you a lot of freedom. So I guess the first image is opened. The second is opening. Yeah, and let's just open the third image. I had just not saved that in the proper location, so I'll just need to take some extra efforts to open it. Yeah, the audible. Yeah, and I'm just opening this. Yeah. So basically, you just load the three images into SiriL. As you can see, the images are pretty large, so it may take some time to load based on how fast your Wi-Fi and how fast your CPU is. But yeah, you can load these three images. So on the right here, you see that you've loaded the three images, the S2, O3, and H alpha. And basically, what you do in GIMP is just try assigning colors to each of these images, just like we did in SiriL. So to do that, you initially have to change the mode of the way you're operating in here. Right now, you're operating in the black and white mode. So just to change that, you just click to image, and there's mode here, and you just change it to RGB. It's initially in grayscale, but you just change that to RGB. to actually play along with the colors, and it's just changing. Give it a sec. Mm, yeah. Ah, सॉरी पीसी भी अभी क्रैश होना था. Just a sec. Ah, या हो गया. But yeah, just a sec. Yeah, so basically you can see on the right here, there's options to open all these images as TIFF files. And yeah, it's still loading for some reason. I have no clue. Yeah, I think, yeah, it's just processing the entire thing. It takes some time for it to go shift from grayscale to RGB. But yeah, you can see you have the three images as TIFF files as S2, O3, and H alpha. And and now that we have changed the settings into RGB, let's go ahead and assign colors to each of the images. So let's start with S2. S2, as we recall, was red in color in the SHO palette. So let's click on S2 here, and let's go to the color settings. On the color settings, you can click on the colorize part. So you can go to colorize the image, and yeah, once you colorize the image, you can basically pick the color you want. So I don't know why, but the default color of it is blue. But yeah, you can change the color. So you want a red color, right? So you can just shift it to, a red color right here. A sec. It shouldn't take this much time. Just a sec. I think I should let the image load first. Yeah. So basically, you just colorize all the individual images, and once you colorize them, you can just play along with a lot of settings. Like you can play along with the contrast of the image. You can play along with the brightness of the image, and basically just manipulate the settings so that you get a final image which is nice to work with. Just a sec. I'm just figuring out what's going wrong. I think मेरे पीसी का skill issue है. Yeah, yeah, it's loading finally, thank God. Yeah. Hmm. I'm sorry about that. Yeah. Yeah, so let's go ahead and actually now colorize the images now once this will load. Just a sec. Yeah. uh, भाई ये लोड हो रहा है, तब तक कुछ डाउट्स वगैरह हुए थे पूछ लो. बट ये हो ही जाएगा थोड़े 20 सेकंड में. बट या यूजुअली आई थिंक तुम्हारा लाइक योर पीसी वोंट बी दिस बैड, आई गेस. माय पीसी जस्ट सक्स. बट या once the images have loaded, they shouldn't give a lot of problems. Yeah, it's finally loaded. Let's go to colors, and as we saw, let's go to colorize. And colorize let's not the initial color is just blue, so let's just change that to a color, a color red, because this is what we want for the image, because it's S2. And let's okay the red color. It'll apply red to it, and while it does, let's just close this image, and we can apply green to the O3 image, and you can apply the Blue, green to the HA image and blue to the O3 image. Just a sec. It's colorizing. Yeah, it's just loading. It'll apply the red color to this, and you can just close this image, and then you can go to the O3 image, and you can again go to colors, and you can colorize it. It's O3, so you want it to be a blue color.
I think you'll have to select O3 just एक बार like
Yeah, yeah, O3 select
yeah.
kara hua, yeah. Colors, and you can colorize the O3. And yeah, O3 is blue, so we can just change it to maybe a little darker shade of blue. Uh, yeah, the point is that you can play along with this. I mean, there's so many shades you can change, and there's just a lot of things you can manipulate and play around when you have these images with. And so yeah, you assign the blue to the O3 as you, and it's just colorizing the image till this finishes. And once this happens, we can apply the green color to the H alpha. Just a sec. Yeah, it's colorized now, and you can close this, and yeah, and you can select the H alpha, and you can apply a green color to it. I'll choose maybe one of these, this shade of green. I guess that should be appropriate. And yeah, you can just colorize it. Yeah, and you'll see that as these images they are just getting overlapped one over each other, so you'll need to also change that setting, because in SiriL we just took that for granted. All the images were just merging to create a really nice final image, as you saw here. But yeah, here you'll have to maybe manipulate the images in maybe. So to change that, we'll have to change the settings of the mode. So let's just do that real quick after the image is colorized. Yeah, now that's colorized, you can just open all three of the images by clicking on the eye icon right here. Yeah. So once you open, you can just see that the red is like overlapping the green and the blue. So to change that, you can see the mode right here. The mode, it's in normal mode, but you have to change this mode to addition so that the pixels actually add each other. Otherwise, as you can see right here, it's just overlapping the image and it's overpowering the image. So you'll have to actually do addition right here. You can change the mode to addition here. You can go here. You can also change the mode to addition. And you can also go to the first image and change the mode to addition. And yeah, once you change all the modes, you will see a final image being created, which is not really good. It's obviously not a very good image. I mean, but it is a baseline image of what you will see for pillars of creation. And but this is where the magic of GIMP comes in. You can actually play along with this image, and you can toy along.
I think your voice isn't audible. Is it just me?
Oh, yes, just a sec. स्क्रीन दिख रही है मेरी? हेलो?
Screen and voice clear है.
Okay, okay.
अच्छा, okay, no problem.
Is my voice better?
Yeah, that was a issue from my side. You can
Okay,
continue.
okay.
Sorry.
Yeah, no problem. So yeah, I was just saying that once you have actually assigned colors and added images, you can see that this is the first outline of the image. But well, it's not a really nice image. I mean, the one on SiriL was just really closely resembling the actual pillars of creation we have seen. As you can see, yeah, this is like the details and the contrast is so much more better. But don't worry, as you can just change all of that. So first you see maybe you need to change the intensities of the colors. Yeah, so you just toy along. Let's just go to the first screen. Let's go to colors and let's go to curves. So you can see the histogram of this image and you can just adjust the brightness of this. So say I want to maybe just increase the brightness of the red color just a little bit so that the image will be so that the image will just have a little more shade of red, because I think there's a little red lacking. If you just compare it with this, there is a little red lacking, at least right here. Yeah, so yeah, as you if you have a reference, you can just change the different saturations by just changing the curves. Then you can also change the curves for the other. Just a sec. Yeah, it's just applying. Yeah. And you can just go on and similarly change the curves for the other colors and the other screens. And once you change the curves, you will just notice a nicer image which will be created. Yeah, it's just applying the curves. Yeah, maybe the intensity of the red, and then I'll just go back to blue. And yeah, I'll just go to colors and yeah, colors, and I'll just go to curves again. Yeah, I think you can see maybe the intensities may be coming along a little better than what there was. And I think you need to increase the intensity of the blue also, because right there in the initial image, the blue was, I think, a much more darker. So you can go to curves again and maybe increase the intensity of blue a little. Maybe not too much. Maybe you need to decrease the intensity of blue and increase of green. So the basic idea is to play along with these curves and just apply all these transformations. And after you have played along with the curves, there's a lot of other settings in the contrasts which you can do to create a final image. So the basic idea is not to create a final image, but just to show that just how much freedom you have in GIMP. So yeah. Hmm. Yeah. Uh, the settings are being applied. Yeah. Yeah, it's just increasing the brightness of certain colors, and you can just it's just playing along so that you have a image which looks similar to this, where the blue is just much more enhanced and shows the contrast between the colors. And just before I end the session, I'd just like to show you one more setting which really enhances the image, just real quick. So you can go to the blue right here, and you can see that the images are really mixed in, and there's no good contrast between the image. And so you can change that. And so you can just go here. You can go to colors. Let this thing just load for like 10 seconds. But yeah, you can go to colors. Yeah, and there's this section for brightness and contrast, and you can just increase the contrast of say blue, and it'll just have such a drastic difference. So I usually like to keep it to 0.1, and you can just apply the contrast, and you'll notice the difference as soon as the settings are being applied. So you can increase the brightness of certain colors, you can increase the contrast between different colors, and basically you can just play along and just create the image you want. So these are the important settings which you'll learn in GIMP. So just to recap, you colorize images, and you colorize images to the color of your choice. You can choose between an entire palette of colors. Then you can adjust the curves of each of the color to adjust the brightness of each of the image. And after you do that, you can adjust the contrast and brightness of each of the screens to make a final image. Uh, yeah, which 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 will suit your tastes and your choices in astrophotography. And that is the beauty of this entire thing. There's no one correct answer for what the nebula or the sky looks like. It all depends on how you want it to look like. And because and well, these images don't really have any color. It's just basically what we as humans have assigned a color to them. And I guess as this is being loaded, you can see just how much better the contrast is now that you have like increase the contrast. It's just already starting to look like the real pillars of creation. And yeah, at least the contrast on the bottom. And you can see them, even the stars are not a glaring magenta. They're just maybe just a little less shade. Maybe there's a little changes with the green. Maybe you can increase the brightness of the green just to make this more visually appealing. But I guess, yeah, this is not the final image by any means. There's a lot of work which needs to be done into it, but you get the basic idea of what you need to do to play along with the tools. So I guess this is all that's for image processing. I mean, the module 4 of the Alona space will be uploaded by tomorrow, and it has a lot more details of image processing, which you will learn. And there's also module 3, which I mean you might have gone through. There's a lot about flats and darks and all of those other objects. And again, this is just the basics of image processing, and there's a lot more detail which goes into this. And yeah, so and you can just play along with it as much as you like, and hopefully you enjoyed the session. Thank you for being patient with that annoying loading time for GIMP. I don't know what happened. It used to load fine, but yeah, thank you for being patient with that. And I hope you will be able to process some of your own images given the data. And yeah, thank you so much for attending the session. If you have any doubts, I'd like to answer them. And yeah, I think Anvit, you can stop the recording. Uh,